Sleep is, yeah, sleep. Yeah, I guess it's necessary. I will begin with a word of prayer. So, dear Father, we thank you for this day and for this time we have to meet and study your creation. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so I wanted to try another one of these kind of exploratory pullback calculations. I'm about 80% through. Well, actually, I don't know how many percent through, but there is a way to intelligently discuss the implicit function theorem using pullbacks that I don't quite fully understand yet. And if you read my notes, they're a work in progress on this point. I mean, there's a theorem that's stated in Harold Edwards' Advanced Calculus book on this point. And I don't fully understand his theorem, but I think it's correct, and I think there's something really interesting there that I think if I could fully unlock, I would understand things more deeply. So I'm just not there yet, but so this is one of those examples that I'm trying to play around with, see maybe if I can get further. But in the meantime, it gives us a chance to, explore the pullback calculation. So I'm going to look at G. It's a mapping from, let's say G is a mapping from R, and I'm using this notation like X, Y, Z, W for my coordinates to R, U, V for my coordinates. All right. I'm basically thinking of this as my M and this is my N. And what I'm going to do is I'm going to calculate the pullback of the top form in the range du wedge dv, right? And as we discussed, this is tantamount to calculating the pullback using the properties here. That's the differential of the pullback of u wedged with the differential, the exterior derivative rather, of the pullback of v, right? But what does that mean? That actually means the derivative of u composed with g wedged with the derivative of v composed with g, right? Which in this context explicitly means we take du, right? So we're taking the differential of x plus y times z, right? And we're wedging that with the differential of x plus y times w. And I'm going to try to be smarter today. I did get my sleep, although I'm unprepared. So there should be some kind of benefit for sleeping, right? Which is maybe doing smarter calculations. And so it occurs to me I can use the product rule. Yeah? Because we're looking at a product of functions, so let's use the product rule. And what that gives me is the differential of x plus y wedged with z, which is just times z, plus x plus y times dz. That gets wedged with the differential of x plus y times w plus x plus y times dw, right? Using the product rule, the graded product rule, with the case of a zero form, right? So we have a plus in the case of an even form. Zero form's an even form. And all right, so when we take the wedge product, you notice that if we're smarter about this, this piece and this piece, when you wedge them, you get what? We get 0, right? So we can really focus our attention on, whoa, that was cool. Oh, yowzers. All right, so that's really the differential of x plus y times z wedged with x plus y times dw, this times that, and then plus x plus y times dz wedged with x plus y times dw. Sorry, I need to think. Did I just, no. Okay, so I'll do some color coding. So this is that one. So I got that with that. This with this is 0, we agreed. Then I go this x plus y dz wedged with x plus y dw. But we still have what else? Right. So we got 3 terms total because that one is 0. And all right, so this gives us, I'm going to factor out the z and the x plus y, all right? And that gives us then dx wedge dw plus dy wedge dw from the first term, right? And then the next one up here, I have an x plus y squared dz wedge dw. And then this one also gives me an x plus y, oh no, excuse me, x plus y times what? dz, x plus y times w, and then I've got a dz wedge dx plus dz wedge dy, right? All right, so let's try to identify common terms and group them. Let's see here. So, for example, dx wedge dw. Where else do we have a dx wedge dw? Anywhere? Nowhere. Okay, so that's just that. What's next? Dy wedge dw. Any of those? Nope, just this one, right? All right, what's up next here? dz wedge dw. We got one of those here. Anywhere else? Nope, just that one. All right, so plus x plus y squared dz wedge dw. All right, what's next here? These two guys, right? So we've got plus x plus y times w dz wedge dx, and finally x plus y w times dz wedge dy, right? Yeah. So this is in a 4-dimensional space. How many 2 forms are there? 6. There's 6 in terms of dimension. The space of 2 forms at a point is of dimension 6. Which one are we missing? We've got x wedge w. We don't have which of that? Which? Oh, so dx wedge dy is missing. All right. All right, let's see if we can understand the significance of that, and perhaps the significance of the coefficients of the 2 forms here. All right? We have a theorem from earlier, which was the implicit function theorem. You guys remember? So that's based on looking at the Jacobian of the map. So let's look at the Jacobian. What's the Jacobian of G? Like, first of all, partial G, partial X, which is what? Z, W. Partial Y, Z, W. Partial Z, X plus Y, 0. Partial W, 0, X plus Y. Right? It should be a 2 by 4, right? So we before talked about like partial G partial xy, right? In our notation, that was, this thing, right? Or we talked about partial g, partial, zw. And that was what? That was 2 by 2 matrix. So check it out. This right here is the determinant of our submatrix, yeah? How about what would this right here? So we'd have, if we look at partial G, partial YW, what's that? That's a 2 by 2 matrix. What's it look like? Yeah, Z, X plus Y, you got your W down here, right? 0. So what's the determinant? Did I do that right, actually? Oh, funky. Oh, my bad. I did the wrong one. This is what? This is actually not Y. This is YZ. This is the YZ. So YZ, because these are the third column, that's W times X plus Y with a what? With a minus, right? Because it's that one. On the other hand, if we were to calculate partial G, partial X, YW, my bad, YW, that's the 2 by 2 matrix. Seriously? Audric. Hey, Audric, believe it or not, I'm teaching it though. Can I call you back? Okay, bye. Yeah, bye. I haven't talked to Audric in a while. See here, Audric is at University of Texas at Austin. He's doing very interesting topology. Let's see here. Partial G, partial YW, where was I? ZW. And what did you say? 0x plus y. Okay, so that one, we calculate the determinant of that guy. What do we get? So do you guys see the pattern? What's the significance of the coefficients of the two of these? They are exactly the determinants of the submatrices corresponding to the columns of the variables being wedged. So actually, what this pullback shows you is all at once, all of your possible choices for implementing the implicit function theorem. All right, this means that so long as these coefficients are non-zero, I can solve for x and w as a function of y and z. I can solve for y and w as a function of x and z. Exactly, we cannot solve for x and y as a function. Cannot solve for x and y as a function of z and w. That's what that all means.
Because the determinants are 0 in those terms.
That's right, yeah. So they're necessarily 0. There's no way out, Yeah. So more generically speaking, if you've got some kind of mystery space and you can pull back a p-form to that space and the p-form is non-trivial, that goes to show you that your space is at least p-dimensional. If it can support a non-trivial p-form, that space is at least p-dimensional. If you can't support a p plus 1 form, apparently your space is p-dimensional. So it detects dimension in this sense, yeah? But anyway, so that brings us on to, so I'm skipping ahead in the notes a bit. So like, logically speaking, the thing I'm about to cover, we could cover later or we could cover now. I'm covering it now because it's heavily dependent on the pullback concept And I think it will give you a sort of deeper appreciation for what in the world pullback's about. And also, this is just really, the Poincare lemma, it doesn't really use integration of forms that much. So I don't think it really uses integration of forms at all. So here's the Poincare lemma. Oh, I'm not stating it first. First, I need to cover a little bit of background here. It's one of those fun times in mathematics where we've named a major result a lemma, you know. So it's kind of funny. As I say in the notes, this section is largely inspired by Gökler and Schucker's, I can't say their names, Differential Geometry, Gauge Theories, and Gravity, which is a wonderful little book that my advisor gave me to read. I asked, it was entirely the wrong book for him to give me to read. I asked him for, I was like, I want to read about why Maxwell's equations are covariant with respect to Lorentz transformations. Like, why is it that Maxwell's equations are consistent with special relativity? He's like, oh, you should read this book. And so I read this book, and I was reading it and reading it and reading it and going, why did he give me this book? It hasn't answered that question. There's another book which answers that question nicely and concretely in the level of like Calculus 3 mathematics, all right? It's Resnick's book on it. But maybe he was just trying to get me interested in other things. I don't know. If so, it worked. It worked. Because this book by Gökler and Schuckler is just a beautiful, beautiful book. Anyway, so getting to the point here. One of the things that I should have mentioned and emphasized is that the exterior derivative, if alpha is a p-form, right, on some manifold, then the exterior derivative of the exterior derivative of alpha is equal to 0. In other words, as some people will sometimes say, d squared is equal to 0 is like a fundamental identity. All right. So the reason for this is pretty much the following calculation, right? If I take alpha is equal to a sum over I, say 1 over p factorial alpha I dxi, right? And I calculate d alpha. Then I have a sum over I, and I'll just pull the sum out if you guys don't mind. Sum over j, 1 over p factorial, partial alpha I, partial xj, dxj, wedge dxi. All right. And then if I take the exterior derivative again, that gives me the sum over I, the sum over j and k, 1 over p factorial, partial squared alpha I, partial xk, partial xj, dxk, wedge dxj, wedge dxi. All right? Oh well. But then the thing is, you guys already proved this in your homework. You know? This right here is antisymmetric in J and K, right? This over here is symmetric in J and K, right? What happens when we contract a symmetric with an antisymmetric? The summation works out to? It works out to 0. So this is equal to 0. Some people have said that every equation in physics can be rewritten as d squared equals to 0. I'm not sure that's really true, but it's a fun thing to say. But there is a lot of physics that can be reformulated in a natural way in terms of the exterior derivative twice applied being 0. We'll see it as we go on in here. So next definition. Given a p-form alpha on M, we say alpha is closed on M. if the exterior derivative of alpha is equal to 0. So a closed differential form is simply one for which the exterior derivative is 0. All right? If there exists a a p minus 1 form for which p minus 1 form, let's say phi, for which d phi is equal to alpha, then we say alpha is exact. And I should say on M. Of course, you could do... What? Why? Goodness gracious. Ay, ay, ay. Ah. Emphasis on I slept last night. I have no excuse, really. I mean, it's Wednesday. Oh, that's what it is. That must be it. It's because it's Wednesday. Very good. I like that. So this is this would make a differential form exact. All right. So kind of obvious proposition. Exact forms are closed. Let me state it in a less, perhaps vague way. If alpha is exact, then alpha is closed. All right? What's the proof? D alpha is d of d phi, right? For some p minus 1 form phi, given alpha is p form, and is exact. It's just the definition of exact, right? And that's 0. Okay, because d squared is 0. So far, so good. So how many of you guys have had differential equations? 1. All right, well, Daniel, you've had differential equations, sort of. All right, so in differential equations, we talk about exact equations, right? So like digression. We say m dx plus n dy equals to 0 is called an exact differential equation if and only if there exists a big function f, which is a function of like x and y, all right, such that the differential of f, which of course is partial f partial x dx plus partial f partial y dy is equal to m dx plus n dy, in which case what? The m dx plus n dy equals to 0 has solution f of x comma y equals to a constant. This is the theory of exact equations and differential equations. Like for an example, we could have, 2x dx plus 2y dy equals to 0. This is an exact differential equation because this is the differential of what? X squared plus y squared, yeah? So my solution is simply x squared plus y squared equals to a constant. That's my solution to the differential equation. All right? And this language of exactness that we're talking about right now is completely coherent with this language from differential equations, right? The differential equation is exact if its defining expression constitutes an exact one form, right? Like if you call this thing, for lack of imagination, omega, then like m dx plus n dy equals to 0, exact differential equation if and only if omega is exact form. Right? Okay, so if it's an exact form, it must also be a closed form. What does the closed form condition mean for our example 1? Closed for omega equals to m dx plus n dy means what? D omega, which is what? dm wedge dx plus dn wedge dy, that must be equals to 0, right? But can we calculate this? This is not a hard one, right? So this just gives me, partial m, partial y, dy wedge dx, plus partial n, partial x, dx wedge dy. What happened to the other two terms? The other term, like partial m, partial x dx, well, dx wedge dx is 0, right? And the other term, like partial n, partial y dy, well, that wedge dy is 0. So these are the two terms that survive. And then, of course, we can put them together as partial n, partial x minus partial m, partial y, dx wedge dy is equal to 0. So you see the closed condition for this differential equation becomes what? Partial n, partial x is equal to partial m, partial y. Or perhaps you saw this as partial q, partial x equals to partial p, partial y if you wrote your differential equation as p dx plus q dy equals to 0. Side comment. So this is a necessary condition in order that you have an exact differential equation. Now here's the question, is it sufficient? Is it enough for the closed condition to hold? Does that imply, actually, that there exists an f such that, df is equal to m dx plus n dy? Well, the answer is no. All right, closed does not imply exact. Generally, closed does not imply exact. Probably the easiest example I can give for you is if we do like minus x dy plus minus y dx plus x dy over x squared plus y squared equals to 0, all right? This actually is the exterior derivative of the angle function, theta. So it's going to be true that d of d theta is equal to 0. That's true. But the rub is that theta cannot be defined everywhere that my omega was defined. See, my omega being this right here. My omega being that right there. Well, omega is defined, what's the domain? You just lose the origin, right? It's the punctured plane is the origin for omega. Again, if you take any formulation of the standard angle, you take the exterior derivative of that formula, you'll get back this. I heard that. So for example, if we set theta is like inverse tangent of y over x, if you take the differential of this, the differential of inverse tangent will give you this. All right? It's not immediately obvious, but if you sit and tinker for a second, you'll get it. Of course, this has a problem at x equals to 0, right? I mean, if you take this derivative anywhere but x equal to 0, it's still going to be true even on the right and the left half plane, although it's not really angle in the left half plane, right? It just only works for the right half plane, for being the standard angle, right? But the larger point is, yes, this is the angle, and yes, it will exterior differentiate back to omega, so it is closed. That's true, no matter which theta you pick. This is just an example theta. However, it's impossible to define a theta that is continuous all the way around in the punctured plane. There has to be some place where your angle jumps by 2 pi. But think about it. If the exterior derivative exists, right, that means that it's differentiable. And differentiable implies continuous. So wherever the angle jump is also a place where it's not differentiable, which means that you can't actually define theta on the totality of the punctured plane. You have to lose some ray where your angle jumps, which is to say that this is an example of a form on the plane, punctured plane. It's an example of a form on the punctured plane which is closed but not exact. So omega is closed but not exact on the punctured plane. Now, in contrast, same example, just think about it for just a little bit more, get a little bit more mileage out of it. If I just said that if I said that this was defined on the half plane, just for x positive, right? On the half plane, positive x, this form is both closed and exact, because this is a potential form for omega. The exterior derivative of inverse tangent of y over x, in fact, gives me this. All right? And as such, this is an exact differential equation if the context is limited to x being positive. All right? So distinguishing between exact and not exact is a picky issue of domain. All right? Yeah. So that motivates then what's the Poincare lemma say? Well, let's write it down. Because the Poincare lemma is exactly about all this. The Poincare lemma says that sometimes closed implies exact. Sometimes closed implies exact. And what's the sometimes? Well, that's where it gets interesting. Because the sometimes is a topological condition. All right? Let me write it down here. Oops, where'd it go? Oh, so I actually have the derivatives in the notes. I guess I gave the same. This is pretty much the only example to give of a form which is, closed but not exact. It's the only elementary example I know. I did soup it up to be three-dimensional yesterday in differential equations. I added a z component to it, but it's the same stupid example. If you add like a z component, side comment here, three-dimensional example. What am I, example 2? Two example ones. But they were part of the, oh yeah, I did. I guess I didn't number this thing, but this was example 2, yeah.
What was the example 2 of digression? Yeah, there was another example.
Well, this was example 1 of the digression, and this was example 2 of the digression. We're now on example 3 of the digression. So my example 3 of the digression would be, you could put omega equal to minus y dx plus x dy over x squared plus y squared plus dz. And this is closed, but not exact, on m equals to R3 minus the z-axis. You recognize this is the same stupid example, though, basically. I mean, you know? It's just like, so, like, for example, we could put phi equal to inverse tangent of y over x plus z, let's say for m plus, which would be x, y, z, such that x is positive, right? So omega restricted to m plus is closed and exact. But omega on the totality of three-dimensional space with the z-axis removed is closed but not exact. Because I just can't extend the angle function all the way around the z-axis. Okay. So these are some examples of what can't be done. And it'll be interesting to look back at these examples and discover how they don't, why it is that we can't find a form. We're going to be able to see why that is as we study this Poincare lemma. And I see I haven't stated the Poincare lemma at the start of this discussion, which is annoying. Well, I think I did, yeah. Give me a second here. If you were a Muppet, you'd be those old curmudgeons that sit in the side box and like say stuff. You're like both of them rolled into one. Do you even know what I'm talking about? No. Okay. Can you be Miss Piggy?
Can you be my Kermit?
Oh dear.
Will you be the Kermit to my Miss Piggy? That sounds like a great Valentine's Day card or something. Or so here's the Poincare lemma. It says if you, oh good grief. Yeah, and it's missing an n, which is much more offensive than that. If U, a subset of Rn, is deformable to a point P, then a P form gamma on U is closed if and only if what? Seriously, this has many problems. Gamma is exact. Ay. Sadness. So much.
You have a point P, then a P.
Yeah, I'm not happy about that. Fine. All right, well, there you go. Now this all begs the question, what on earth do I mean by deformable to a point? All right. That definition is actually given before that, but anyway, we'll get back. This is Poincare's lemma, though, and we'll kind of we'll get back to what I mean by deformable to a point at the end of this discussion. All right. So you're just gonna have to wait. So, do you want me to state it? I can do it now.
I do.
All right. So the definition to make sense of the lemma, what do we mean by deformable to a point? Definition, subset of Rn is deformable to a point P if there exists a smooth mapping G that goes from the unit interval across the space U to U again, such that G of 1 comma x is equal to x for all x in U, and G of 0 comma x is equal to P for all x in U. So we can. So this, and I think there's something missing here, which is probably important, which is we assume. Where is P? P is an element of U. All right. Yeah.
And the interval must contain 1.
Oh, this I is 0 to 1. That's the unit interval. Good question. So I can draw a picture of this. Like, what is the Cartesian product of U and I? So I'm going to draw it like vertically, but you might draw it. Anyway, so this is the picture I'm going to draw. So here, so here's a copy of U on its lonesome. Over here is I cross U. I'm drawing the first component as if it's vertical because that's where I can draw better. So I guess I should have reformulated the whole thing so that my picture would be consistent with the math, but whatever. We can make X go this way, and then Y and Z or whatever. Anyway, the point is, up here, you just have, up here is maybe, so if I'm calling the input to G, like generically T comma X, all right? So up here, you'd have T equals to 1. Down here, you have T equals to 0. And as you go on, so first of all, it's just it's just like from here to here, right? We're just talking about the identity map on U. That's what we get if we take G and we just put in 1. Right? It's the identity map up here. But by the time you get down here, we no longer have the identity map. We have what? Down here we have the constant map. Constant P map, which is gotten from this. And this is smooth, right? So we have this smooth interpolation from the identity map all the way down to the constant map. That's what we mean by deformable to a point. It's a way of making precise mathematically the concept of being able to take U and scrunch it to a point. Now, at first glance, you might not see what on earth this has to do with the thing we started today with, right? I mean, after we got past the implicit function theorem business, but. All right, so let me go through the argument. This is not my argument. I found it in Flanders. There's a book on differential forms by a guy named Flanders. And this was born, how dare you? And this was born out of a joint math/engineering seminar in the 1960s at Purdue, of all places. So I guess the engineers at Purdue must have been pretty formidable in the 1960s, I guess. I mean, for this book, the Flanders book on differential forms, to have born out of a math/engineering seminar, like it's fascinating to me. But I really don't think that this argument is due to Flanders. I have a strong suspicion this like goes back to Cartan or something. I don't know the exact history, but here's what we're going to do. All right, so we're going to suppose U is a subset of Rn, and I is equal to 0 to 1. Typical point t comma x in I cross U. All right. We'll define maps. J1 is a mapping from U to I cross U, and J0 is a mapping from U to I cross U, whereby J1 of x equals to 1 comma x, and J0 of x equal to, well, 0 comma x. All right. Both of them for all x and u, okay? So you might recognize, well, let me draw another picture over here. So basically, why did I do that? Yay. So if we want to think of it, this would be like J1, and this would be like J0. All right? Because I have t equals to 1 up here, t equals to 0 down here. And again, this is a picture of I cross U. All right. So we can pull back forms on the cylinder to U. All right. And we can pull back. So we can pull back forms on the cylinder. What would a differential form on the cylinder look like? So a differential form on cylinder has, you know, we could say dt wedged with dxi, right? Where, you know, I is some element of, you know, where the size of this is at most n, you know. What I'm trying to say is, you know, U is a subset of Rn. This is an abstract picture, right? It's like an interval crossed with a subset of Rn. So I'm drawing the picture three-dimensionally, but understand that this space, you know, if U happened to be a subset of 4 dimensions, we could support a 5 form on here, like a time wedge a four-dimensional space form, you know. Yeah, that's not going to be a problem. So we will not be confused about the multi-index I versus the interval I. There's no danger for confusion there. I don't think. So, okay, so for example, if we look at, if we had, say, omega was equal to x plus t, all right, x plus t dx plus dt, right? This would be, you know, a one form on I cross u, right? We can pull that back under J, right? So you guys tell me, what would the pullback J0 pullback omega, what would that be equal to? And what would the pullback under 1 of omega be? This isn't really part of the proof. This is just trying to make sure we're all understanding each other. So if we think about pullback under J0, right? Think about it sort of, this is my t, right? This is my x. This is t, this is x, right? So pullback under 0, I put t equals to 0, right? So it just pulls back to x dx, all right? So we're just substituting t equals to 0 and x equals to x into the x pullback is kind of dumb, you know? All right. How about 1? What will we get? Yeah, still just an x, right? But what then? X plus t, which is 1. So remember, U is a subset of Rn. So like what's happening, the pullback under J1 or J0, we're pulling back to a n form, or an up to n form. It could be, we're pulling back a k form, possibly, where k is less than or equal to n into U. So, but these are both differential forms on U, right? You could just as well make this, you know, dx wedge dy wedge dz. The same calculation would go through with dx being replaced with dx wedge dy wedge dz, all right? So that's what the pullback, what I'm trying to tell you guys, is the pullback under J0 or J1, they're pretty easy to understand. Okay, we just essentially substitute in t equals to 0 or t equals to 1. That's the substance of it. All right. So next up, we'll define smooth mapping K You probably left class to get batteries for that. That's probably what it was. P plus 1 forms on I cross U to P forms on U. All right? And here's how we're going to define it. So K, number 1, K acting on A, which is possibly a function of t and x, to dxi, where dx multi-index I. Again, no danger of confusion with the interval I. I'm trying to will that statement into existence. So this is just going to be 0. On the other hand, 2, if we have k of some function of t and x, let's say a, times dt wedge dxj, where apparently dxj must be a form of less degree than, well anyway, like this dxt wedge, dt wedge dxj, then we're going to do something interesting. We're going to destroy the t by integration. Integrate from 0 to 1 of a of t comma x dt dxj. all right? So we we take the purely spatial form and just send it to 0, but that's still a p minus 1, a p form, great. And we take this kind of p plus 1 form, which is kind of more interesting one, and we just squish out the t by integration. All right. And then extend linearly, all right? Extend linearly off these formulas, we can do that, all right? Because we've defined how it works on the monomial basis. So there you go. Now, the K-lemma which I guess I'll have to state over there. We may have to go to the sideboards today. All right, so the K-lemma it says that if omega is differential form on I cross U, as we've been talking about, then K acting on the exterior derivative of omega plus the exterior derivative of K acting on omega is equal to the difference of the pullbacks under J1 of omega and J0 of omega. And the proof is going to divide into cases. Since the equation's given for linear operations, it suffices to check the formula on monomials, since we can extend the result linearly once those are affirmed. All right, so there are two basic categories of forms on I cross omega, right? So what's case one? We could have something like omega is A of t comma x dxi, right? Where, you know, dxi is a p form, yeah? What happens when we calculate d omega in this case? D omega is what? We just have I guess, well, there's two terms, isn't there? Here's two terms, right? Yeah, there's two terms. So the one, I'll start with the spatial part. Sum j equals 1 to n of partial a partial xj dxj wedge dxi, right? But then plus partial a partial t dt wedge dxi, yeah? So there you go. There's my exterior derivative of omega formula. Now I guess I'm supposed to calculate k of d omega. So let's do that. What is k of d omega then? So first of all, let me give those things some labels, because I don't want to write it all again if I can help it. Yeah? So this part is 1, this part is 2. Notice that 1 is 0 because it's purely spatial.